Alright, so now we're going to talk about the law of conservation of mass. So in the 1700s, Antoine Lavoisier, he placed a carefully measured amount of solid mercury oxide into a sealed flask. He then heated the compound, produced liquid mercury and oxygen gas. When this chemical reaction was finished, Lavoisier measured the mass of each of the products. So he found that the total mass of the two products was identical to the mass of the reactants. The following word equation shows the reaction, along with the masses of the reactants and products. So this is a simple decomposition reaction. We have solid mercury 2 oxide. He had 10 grams of that. And it turned into oxygen gas, in which he had 0.7 grams of that, and liquid mercury at 9.3 grams. So Lavoisier concluded that the atoms in a chemical reaction were just rearranged, not destroyed, and the conclusion is known as the law of conservation of mass, which states that in a chemical reaction, matter is not created nor destroyed. If you start with a reactant of 10 grams, you will end up with 10 grams of product. So, staying balanced. When chemists write chemical equations, they do not usually use word equations. When dealing with chemicals, this method is not exact enough. Using a word equation would be like writing this word equation on how to build a house. So you would say that energy plus wood plus concrete plus steel plus metal is a house. The builder of such a house would have so many questions. How much of each material would they need? Chemists feel the same way. They need to know the exact amount of chemicals used to produce the chemical reactants and are used in technological processes. These equations do not state the quantities of the substance needed. They also do not reveal the types of atoms involved. So when the chemical formulas of the reactants and products are used, then you can determine exactly what atoms make up the reactants and products. So checking and balancing equations. A balanced chemical equation has the same elements and the same number of atoms of each element on both sides. We do this by adding coefficients, so the large numbers before the chemicals in the formula. And we've been using this as our example. So we have the reactants of hydrogen and oxygen producing water, and there are coefficients there are 2. So saying that we need 2 dihydrogen, so two molecules which are made up of 2 hydrogen atoms each, so giving us 4 hydrogen atoms in our reactant side, plus we have the 1 molecule of oxygen where we have the 2 oxygen atoms together. So that means in the reactant side we have 4 atoms of hydrogen and 2 atoms of oxygen are going to give us 2 molecules of water, where we would then have, again, 4 molecules of hydrogen and 2 molecules of oxygen.